What do you think? Everybody got it? I think we said it about 20 times yesterday, but what is it? Moles of what? Solute over liters of what? Solution. You know, one time, I don't think I mentioned this to you yesterday. See if I can find it. There was a unit, and when I took chemistry, they made us learn this one too. And if I do, oh, you're right. Thank you. Okay, they made me learn this one because I think what happened is the chemists knew that the mole concept was really big. And so I think what happened is they kind of want to work their way into it. I don't know the whole story here, but this is a thing called molality. Not molarity, but molality. And look at the definition difference. Moles of solute, moles of solute. Kilogram of solvent. That means do you know a kilogram of water is a liter of water? Do you know that? A liter per kilogram of water, for example. But see here, I don't know how much water there is. It didn't say liter of water. It's liter of what? Water and solute. Everybody get that? So this is a nice little thing they had to try to get into the mole world, but they found out this is not good enough. And this is the one who's the star of the show. So anyway, molarity is moles of solute for liters of solution. We got that. All right, so now we had a problem here. Take a look at problem number 1 again. Calculate the molarity. You say, calculate, I need moles, I need liters. What did they give me? Oh, they gave me grams. So what do I have to do? Help me out. I got to get going a little faster, okay? What do you think? Change grams to moles. Oh, they gave me milliliters. Change milliliters, liters, and I'm done. I can do it, okay? Next problem. How many grams? How many grams are needed? Wow, I don't know what to do. I don't know what to do. Well, if we take the same equation and rearrange it, what is molarity times volume in liters? What is molarity times volume? Moles of what? Okay, now look at problem number 2. Let's say it's a test question. Molarity, volume. I get it. Molarity and volume. Molarity times volume is what? Not grams. It's moles, isn't it? But that's close. If I get into the mole world, do I know how to quickly change from moles to grams? Well, then I can do it. I love the thinking aspect of this, where it's a little problem solving. You said, "Are you going to do this way?" I can do it. I can find this. Look at number 3. How many grams? Look, they gave me molarity and volume again. Ding, ding, ding. Molarity times volume is moles. Change moles to grams. Find the molarity. Oh, well, molarity is what? Moles over liters. Okay. They're going to give me grams? Oh, I'll change that to moles. Are they going to give me liters? I'll keep it. I'll keep it. If I can get you to build your confidence up, you say, I can do that all day. I can do those kind of problems all day. Well, then we did, I don't know if did your class get to this one or not? I don't think the other class did. Do you guys get to it? Okay, so now, we showed you a picture in the book where and my advanced chemistry students, they actually do make their own solutions. I never got to, but I make them because they will make a standard solution. They'll make one, and they'll say, this is 1.00 molar NaOH and it's 500 milliliters of solution. And they do it very carefully. And they actually use this in an experiment, and they better have done this right. If they didn't do this right, the whole experiment's messed up. And they do it right. So now, let's go over here. What if, instead of them making it from chemicals, like so many grams of NaOH and so much water, what if I have something that's already made up? What if I have a solution that's already made up and it's fairly concentrated? Did I do this yesterday? I'm going to make double sure. I happen to have a bottle back there of, I think it might be 14 molar sulfuric acid. And I can tell you right now, that will hurt you. It will hurt you a lot. And I have to be careful. I always have goggles on, always. When I have goggles, that stuff can hurt you. And so I want to save the school a lot of money, and I can do this. So what I'm going to do is, I don't want my students messing with 13 molar or 14 molar sulfuric acid, and I don't need that concentration for the experiment to work anyway. I don't need it. So what I have to do is I will make a dilution. So if it was 13 molar, it's not going to be 13 molar when I get done. It's going to be less than that, isn't it? Everybody with me? So what's the equation? I love the equation. You know what I didn't get a chance to ask? And let me see if I have any money today. So, oh yeah, I got one. I'm gonna do that. Well, it's only one. It's only $1. All right, so here I'm gonna ask you a very high level question, and I'm gonna see if you can figure this out. I'm going to take a certain amount of this, and it's very concentrated. I'm going to put it in a container. I'm going to add some water, and it's going to dilute it. When I get done, I'll have my final solution that is not as concentrated, and I'll have a certain amount of it. Right? My question to you, for $1, it's like Jeopardy, why does this equation work? Why is M1 times V1 equal M2 times V2? And I'll let you answer. I'll take the first max. Ooh.
Is it keeping the same ratio?
Say it again.
Is it keeping the same ratio?
Keep going. Well, at least you broke the ice. If you want to come back with another one, you can. But I'm gonna say no so far. That was not bad. That was not a bad start. Why does M1 times V1 equal M2 times V2? You want to try it?
Because it's a ratio of concentration, right? Like how concentrated something is based on its molarity and the volume is going to be the same with its concentration in another volume.
But is the concentration of that the same as that? No, they're not the same. Keep thinking. Keep thinking. I love two people took a chance. Anybody? keep anybody? One more? Take a chance. One more? Nobody? You don't even take a chance? Okay. You sure? Okay. Thanks. All right. So, last chance. Okay, here we go. When I take this out, does it have a certain molarity? Doesn't it? Yeah, didn't it? It has a certain concentration, right? And it isn't a certain volume? Okay. What is the molarity of that material times that volume of that material? What does that equal? So, little bell didn't go off in your head. What's molarity times volume? Now you're killing me. What's molarity times volume? Moles. Okay, so guess what? When I do that, I took a certain number of moles out of that bottle, didn't I? And what did I do to it? I put it in another bottle, didn't I? And then I added some water. But did I add any more of that chemical? So how many moles of that chemical are in the second bottle? Now, I didn't mean moles of water. How many moles of that chemical are in the second bottle? The same. Isn't that right? And that's why that works. The moles of that chemical here are the same as what? the moles that I took out here. Concentrations aren't the same. Okay, that might have been a little higher level, but that's why that works. So let's try one. Now you said we already did this one. Are you sure? Okay, all right, let's do the next one then. If I add 25 milliliters of water to 125 milliliters of blah, 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 what will the molarity of dilute, blah, blah, blah. Okay. This is a dilution problem, isn't it? All right, now we just have to figure out who's who. All right. What do you think the original molarity was? Okay, there we go. 0.15 big M. What is the original volume? How much of that stuff did I take out? Uh-oh. Oh, yeah. I'm losing it. Hang on. Try it again. Look at the problem again. Did I take stuff out of the original material, out of the original solution? Aha. I see. What do they want me to find? Tell me that. What's the final answer going to be in? Is it going to be M1, V1, M2, or V2? What's the final answer going to be in? What will be the... So they want me to find that right there, right? Then they better have given me this, this, and this, right? Let's try it. Let's go find them. We found that one. What's that? They had to give it to me. They had to. What you got, Elizabeth? What you got?
0.125.
Say it again?
0.125.
Okay. Now, I'm going to show you a little trick. Even though molarity times volume in liters gives you moles, you don't, for the dilution equation, you don't have to change it into liters. If you want your final answer to be in milliliters, leave it in milliliters. So I'm going to do it both ways. If you want to change it to liters, you can. But I'm going to go ahead and make it 125 milliliters, and I'll show you what happens. Now, they want me to find M2, don't they? So I don't know that one. Now, oh, here's a tricky one. What is the final volume? Go ahead, Elizabeth.
It is 0.15.
Excellent. Excellent. Isn't that right? Or I could also say 150 milliliters, right? And 0.515, I'm okay with that if you want to do liters. Now, so anyway, I'll tell you why it doesn't matter on these. On the dilution equation, you don't have to change it to liters because guess what happens? Milliliters cancel out. So I don't have to do the extra step and change it to liters. You get it? And what's the only label left? What's the only label left? And that's what I want to find, isn't it? Okay, one more time. If you molarity times volume in liters does give you moles. You do have to have liters there, right? But you don't have to change it to liters when you're doing these. All right, everybody know how to do this? This times this, divided by that. This times this, divided by that. All right, let's try that. What's the answer? Elizabeth, you did great on that one.
I got 0.125.
Point what?
125.
125? What's your label?
Polarity. Big N.
What is it?
Big N.
That one? What's big M mean?
Polarity.
Okay. So it's a 0.125 molar solution, isn't it? So the final molarity is 0.125 molar. Now, I keep looking at your faces. I just need to know what's going on here, all right? That was a little bit of a tricky question because they took 125 out, but then what they add to it, 25 milliliters of water, they should have diluted it, shouldn't it? If the original molarity was 0.15, this should be less than 0.15, shouldn't it? It's more dilute. All right. All right, try the next one. If you want to sit with somebody, I want you to try number 7 and number 8. Try number 7 and number 8. Now I have another question today, so I'm going to keep this dollar out. I have another question today. Go ahead and do number 7 and number 8 with somebody else.
Do you have an answer?
Yeah.
This is the answer. You just did 7.
Yeah, no, just the 6. It's like below it.
That's below it. Okay, alright.
it's kind of like a little puzzle. You're trying to go find the pieces. What's the name of that piece? What's the name of that piece?
You multiply 245.
Is the acid-base like neutralization problem gonna be on the fish?
How do you set it up?
Maybe, but we're gonna get to that next. So,
Yeah.
and you know what? It looks just like that. It's just a tiny bit different.
Okay.
But we'll do that. We'll do some of those problems today too. So,
And then you
I don't even mind if we. Well, we'll see.
What do you get?
All right, how's everybody doing on number 7? Number 7 is like a reverse dilution problem, isn't it? If they let the water boil away, any of you here cook? Anybody here cook in here?
Occasionally.
Are you do okay? Can you tell everybody as a cook why would some people take something in a pot and let it boil for 30 minutes, or what happens to that soup or whatever if you let it do that? It gets more concentrated. Why? Because when you boil it, what's the only thing that leaves is the water. So if a cook wants something to have more intense flavor, more concentrated, they'll actually boil it down a little bit, and now you know a little bit about how that comes into play with cooking. That's very good. So you knew that. That's really good. All right. Everybody look out here, and this is like a reverse dilution problem, so I am going to use M1V1 equals M2V2, and I'm going to look real quickly here. What does it say? What will the molarity of the final solution be? Here we are again. They want me to find that. You better give me that, that, and that. So let's go looking for it. Oh, look. That's 345 milliliters. I don't have to change it to liters. And it's 1.5 molar. That's the molarity. All right, I'm getting there. And then what's the final volume? I boil it. It used to be 345. What's it now? Whoa, only 250. Woo, boiled that thing down, didn't I? And you know why I don't have to change it to liters? Because watch. Boing. See, they cancel out anyway, don't they? All right. Anybody have an answer for this? Who? Let's give me an answer. John, you got this one?
2.07.
What label?
Big.
Okay, molarity, right? Molar. Now, if he's right, this should be more concentrated than when we started. Not less, but more. And to start out as 1.5, there you go. That looks reasonable to me. That sounds reasonable. It's more concentrated, isn't it? All right, let's do the last one. Let's see. I add water. Oh, there it is. What is the molarity? Okay, so that when we find that again. So what is the first molarity? 0.15 molar. And what is the first volume? Uh-oh, careful. What was the first volume? Wait, I add 100 milliliters until the final volume is what? Well, then what was the original volume? And look again. If I add water, to 100 milliliters, I'm sorry, my fault. 100 milliliters is the original volume, and then what's the final volume? 150. Okay, so it should be this times that, divided by that, and Max, what you got for that one? 0.1 label. Okay, molar. Okay, 0.1 molar. Is everybody getting that? 0.1 molar. What do you think? Pretty easy. All right. All right. What I'm going to do now is I need to show you the last mathematical part of the chapter, and we need to go to right there, section 15.7, And if you want to read this tonight, you can, but I'm going to teach it to you, okay? It's called neutralization reactions. And let me go back. Let me get this out of the way. These equations are essentially the same thing. The one you just did for dilution. For a dilution equation, M1 V1 equals M2 V2. Okay, now, here's a new one for you. Acid, base, neutralization. Now, those are solutions. Acids and bases, by their definition, are solutions. And let me show it to you. Whoa, wait a minute. That looks kind of familiar. That looks kind of familiar. And so, if I'm pretty good with the dilution equation, I should be able to use this one because it's very similar. Now, remember yesterday we talked about part of the test, a lot of it's mathematical. What's the other part of the test? Conceptual, isn't it? So you have to know something behind this. So I want to show you something real quickly. I'm going to take the most famous acid-base neutralization you can think of. I'm going to take hydrochloric acid, and I'm going to mix it and react it with the most famous base in the world, sodium hydroxide. Tell me what do I get here. Kaylee, you can do that. It's a double replacement. Say it again. It's double replace. Water, yes. Yes. Nice. Now, if you were to look in a book, it says anytime an acid and a base neutralize each other, you always get water. You always get water as a product and a salt. Now, it just happens, it's a coincidence that I get the most famous salt in the world. Every ionic compound is a salt, isn't it? But it's just a coincidence that the salt here is the most famous salt in the world. Now, this one's already balanced, isn't it? Yeah? Okay. Now, what I want to show you is, you didn't like this, but remember how we did the complete ionic equation? Let's do that again. Let's do that again. This is aqueous, isn't it? Acids and bases, by definition, are solutions. They are solutions that have things in them. This is going to be aqueous. All right, let's try it. You remember this? Remember how we did that? The complete ionic equation. When you put this in water, what's really floating around that beaker? Hydrogen ions and what? Chloride ions, right? And they're dissolved in water. And sodium ions dissolved in water, plus hydroxide ions dissolved in water. And what about this? One of the driving forces is the production of water. So I'm not going to take you apart. And it just so happens that this is aqueous. So what am I going to do here? And okay, that was a complete ionic equation, right? Now what came after that? What came after the complete ionic equation? Let me see, Noah Ramos. Let's see if you remember. What's the next thing we did on that chapter? After the complete ionic equation, what did we do? What was it called?
Did you just cross out the ones?
What is it? Yes? Say that?
Cross out the ones that are
What are they called?
not much.
Okay, you're close. We want to do the net ionic equation, don't we? And how do you get to the net ionic equation? Cross out the, you couldn't remember that word, could you? The ions that have nothing to do with the chemical reaction. They just sit around watching it like people come into your baseball games or to your swim meets. What are they called? Cross out what? Cross out, somebody said it. Spectator ions. Remember that? Okay, here we go. It's fun. Oh, hey, you're the same on the left as on the right. You did not do anything. You had nothing to do with this reaction. Hey, look at that. What did you do? You're a spectator. I think I'm done. And here's what's neat. Here's what's neat. All acid-base reaction, neutralization reactions, here's what happens. The net ion equation looks like this. The hydrogen ions react with the hydroxide ions. This is what makes an acid, by the way. This is what makes a base. And what happens to them? When they get done, they're not an acid or a base, they're neutral. They've been neutralized. All right. Now, here we go. Is everybody sort of on board here, right? When, remember we had indicators? Remember we showed indicators at the beginning of the year? We had this indicator called phenolphthalein. If I put an acid, it'll stay clear. If I start dropping some base in there, drop the base, no. If I start dropping the base, do they still say that? Drop the base. If I start dropping the base in there, it'll stay clear. It'll stay clear. And you know what? Because there's more hydrogen ions than OH. Drop some more base. Okay. And now I add one more drop. And what happens is, as soon as I have more OHs than H's, then it'll change pink, and I'll know that I just went right past the neutralization point. So here, when neutralization takes place, what can you say? What can you say? What's that number there? What's that number? Yeah, one more time. One more down. Why is this true? Why does this work? I'll give you a clue. It has something to do with that right there. Why is this work? Why does it work? All right, take a chance. Take a chance. Really? Nobody? Nobody? Come on. You're honors chemistry students, right? Okay. Why does this equation work for neutralization? Ooh, it's a little disappointing to me. If I hadn't already explained why the dilution equation worked, I might be okay with this, but I'm not okay. After I explain why the dilution equation worked, and now you have no idea why this one works? I'll give you 15 more seconds for somebody to take a chance. You can't lose. Yes?
This might be stupid, but is it because they're equal on both sides?
Wait, say it again.
Is it because they're equal?
What's equal?
Like, which one?
What?
Like, the amount on both sides.
Wait, say it. What's equal?
Like, I don't know how to explain.
Well, I want you to tell me. What's equal?
Like, the mass of them?
No.
Okay.
What do you think?
The moles,
Of what?
ions,
Which ion?
the hydrogen.
Are equal to what?
So the hydroxide ion.
All right, here you go. Sorry, it wasn't grams, but what is molarity times volume again? Moles, right? Now look at this equation. You were close, okay? It's not grams though. Watch. See the coefficient? When you have the same number of moles of hydrogen ion and the same number of moles of OH, everything is neutralized, isn't it? And what's M times V? It's moles, isn't it? This is moles of hydrogen ion. This is moles of hydroxide ion. And when they're equal, then you have neutralization. So here's the trick. There is a trick to this. If I were to tell you, I'm going to show you a problem here. Well, we'll do one on the paper. Let's do one on the paper. Okay, all right, let's go over here. Now, let's take a look at this one. what volume, blah, 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 is required to neutralize, blah, blah, blah. Okay, now I know it's an acid-base neutralization, so I'm going to do this. The molarity of the acid times the volume of the acid. Remember, that's moles. Isn't that moles? Moles of what, though? Don't forget this. Moles of what? What does this equal? Moles of what? What specific ion? Hydrogen, isn't it? Times the molarity of the base times the volume of the base. Now, this is the tricky part. This is the tricky part, and that's it. There's one little tricky part. That's all. Here we go. If it is 0.075 molar HCl, here's my question for you. What is the concentration of hydrogen ions? What is the concentration of chloride ions? We did this yesterday. I know the concentration of HCl is 0.075. What is the concentration of hydrogen ions? Jonathan? That's right. And what's the concentration of chloride ions? For every one of these, there's one of those. For every one of these, there's one of those, so that would be the same. Now, it just so happens that I really don't care about the chloride ions. I don't care about you. I do care about that. That's what I put in here. When I say molarity of the acid, it's really the molarity of the hydrogen ions, so the lucky, I can put that number in here. Whoops. All right. Now, what volume of acid? I don't know. They're not going to tell me. All right, so you're my unknown. And what am I trying to neutralize? Okay, now here we go. What does it say? 0.01 molar CaOH. Okay, be careful. What is the concentration? Let's see, who's going to call him? Ethan. What is the concentration of calcium hydroxide? I'll give you that one away. It's 0.01 molar. What is the concentration of calcium ions? 0.01. How do you know that? Because for every one of these, you get one of those. Match. All right, see that? Now, here's a tricky one. Look out. What's the concentration of hydroxide ions? Go ahead, Ethan.
Is it the same?
Could
Or
be
is
the
it
same.
0.02?
How'd you get that?
Because it's 2.
For every one of these, you get what? 2 hydroxide ions. So even though you think it's simple, you said, oh, find the molarity of the base and just put it in there. Just plug in 0.01. It's not really the molarity of the base. It's the molarity of the ion that made you a base. You get that? And how long does that take? How long does that take to say, ding, 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 you had 2 hydroxide ions. I'm going to double the molarity. You get it? So I don't write 0.01 for the molarity of the base. I write the molarity of the ion that makes you a base. And that's the only trick that we have here. And by the way, I'm going to leave it as milliliters. Why? Because this equation, if I want my final answer to be in milliliters, I'll leave it as milliliters. I do that in your calculator and see what you get. So it's going to be this times this divided by that. This times this divided by that. Max, you're done? What do you got?
26.7.
How much?
26.7.
What units?
Milliliters.
Right. You know why? Because big M canceled. Wait a minute. Big M canceled out, and the only unit left is milliliters, right? So if you want your final answer to be in milliliters, leave it in milliliters in the original equation. Get that? One more time. When do you have to change milliliters to liters? When? Which one of these equations do you have to change it into liters? Which one? I mean, we have to have liters here, right? But we have to have liters here because molarity times volume in liters is the only time you get moles. So that's the only time you're required to change it to there. All right, let's go ahead and do the next one. Do the next problem. You know what's interesting about the next problem? It's easier because how many hydrogen ions are in the acid? 1. And how many hydroxide ions are in NaOH? 1. That made it easy. All right, check with a neighbor and see if you get the same answer they did. And as a matter of fact, this question was way easier because I didn't have to worry about multiplying by 2 or anything like that. All right, Danielle.
So like in number 9, how the concentration is different for the
For the OH?
You always use the bigger one?
I always use what?
How one is 0.01 and then the other
Okay.
one is 0.03.
So here's what happens. What's the concentration of calcium hydroxide? 0.01 molar. But what's the concentration of calcium ions in there? Well, for every 1 calcium hydroxide, how many calcium ions do you get? 1. That's why they match. They're going to have the same molarity. 1, 1. But how many hydroxide ions are there for every 1 calcium hydroxide? There are 2, aren't there? So for every 1 calcium hydroxide, you get 2 hydroxide ions. So what's the concentration of hydroxide ions? Twice as much. And by the way, I don't really care about the concentration of the calcium ions because that has nothing to do with acid-base neutralization, does it? I had you write it down, but what I really want is the concentration of what? This? And for every one of those, how many hydroxide ions do you get? You get 2. So there must be twice as many hydroxide ions as there are calcium hydroxide particles, big things. So that's why I had to multiply that by 2. This one was an easier problem because guess what? For every one of these, how many hydrogen ions do you get? 1. So what's the concentration of hydrogen ions here? 0.115 molar. 1, 1. What about this? How many hydroxide ions are in there? 1. So what's the molarity of hydroxide ions? 0.0875, right? What do you think? So that's the only trick. And I know some people, every year they take this test, and they think these are identical. They're not identical. First of all, this is a real chemical reaction taking place, isn't it? What's this? What are you doing here? This is a real acid-based chemical reaction trying to neutralize each other. What's this? Is this a chemical reaction? Or are you diluting something? That's not a chemical reaction, is it? And so people, because they look so similar, they think they're identical. It's true. I do have to maybe multiply, divide, but I do the math kind of the same. The only thing that makes this different is they say it's the molarity of the acid, but what they really mean is the molarity of the hydrogen ion The molarity of the hydrogen ion. And this means the molarity of what? Of the hydroxide ion. And that's the only trick. If you give me a problem like this one, then I'm easy. For every one of those, there's only one of those. So whatever the molarity of HCl is, that's the molarity of the hydrogen ion. Whatever the molarity of NaOH, that's the molarity of hydroxide, because there's only one there. But the one we just did, oops, there it is. For every one of those, you get 2 hydroxide ions, so the concentrate in that must be twice as much. Okay. Now, I'm going to show you a problem that the person who wrote this, I really like this practice test because they're going to sneak up on you, okay? This is an easy problem, but they're going to sneak up on you. I want you to do that problem there with a partner. I want you to find a partner, and I think you're going to have trouble getting that right. So they gave you kind of a hard one there on this practice test. This one has nothing to do with moles. Nothing. All right, this is how they did concentration units without the mole, and it's just percent by mass. You're going to have trouble getting this one right because I thought they're kind of sneaky about the way they did this problem.
And we need to get grams and kilograms.
Water is a solution, right? So it'd be 200 divided by 100.
Yeah, and what's his trying to
Yeah. Well, percent by mass.
Now remember, it's just kind of a throwback question because it has nothing to do with the moles or it has nothing to do with molarity. It's just percent by mass.
So they gave us that. So it was usually.
Okay, everybody got it? Raise your hand if your group has an answer. Oh, okay, keep going. All right, keep going. They made this problem a little bit harder just to see what you do, but I kind of like that they gave you one you had to really think about. I have almost none of these, maybe a couple on the whole test. All right, anybody have an answer yet? Uh-oh. All right, I'm okay with that. But I'm gonna give you a little bit more time. Anybody have an answer? All right. Tell me what made you get stuck then? Percent by mass is, you don't have to worry about molarity or moles or anything like that. But what you should have had was the mass of the solute divided by the total mass of everything. Did you get that far? Okay, what is the mass of the solute then? What was the mass of the solute? Did everybody get that far? Now, what's the total mass? Did you know that 1 kilogram is 1,000 grams? Did you know that 1 kilogram is 1,000 grams of water? When you put this and the water together, what's the total mass? Okay, and then times 100 to move the decimal over. What do you think? Is that what got you stuck? The 1 kilogram, is that what got you stuck? That should be it right there, shouldn't it? It's the grams of solute over the total grams of everything, solute and water, isn't it? All right, go ahead. What is the answer? Anybody have it?
18.3%.
Well, that's not okay. 18 point what?
3.
Okay. Is that what everybody's getting?
Yes, sir.
Oh, now I don't. The only thing I didn't like about that is after doing all these molarities and neutralization things and dilution questions, it gave a throwback question back to percent by mass, which is what we started with. Remember that? And that was the easiest one. You just had to remember you divide by the total mass. But the total mass was tricky because I had this mass, and I also had 1,000 grams of water, didn't I? All right, we got about 4 more minutes. Let's look up here. I'll tell you what. I'll go right down the row. Caroline, I'm going to read the question. You tell me which word you think they're talking about. Number 12, blank, the substance dissolved in a given solution. What? Yes, E, solute. All right, next, Madeline. Blank expresses the mass of solute in a given mass of solution. Say it again. I couldn't hear you.
Said mass percent.
Yeah, that's it. As a matter of fact, we just did a mass percent problem, didn't we? All right, Jonathan. Blank. A solution contains as much solute as will dissolve at that temperature. Yes, you guys are good. You guys are good. Next, Noah. Blank, most commonly used expression in the of concentration describes the amount of solute in moles and the volume of the solution in liters. Yes, very good. Where's that at? H? Even though the most common one for the solubility graph, it's not common overall. The star is molarity, for sure. Next one, John. Blank, acid-base reaction. Yes, very good. All right, next, Max, skipped you. Molarity equals. Moles of solute or what? All right. All right, next one is Noah Ramos for dilution equation.
M1 times B1 equals M2 times B2.
Nice, very nice. All right, next one, Tyler. MA times VA equals MB times VB is an equation for what? Say it again. Yes, acid-base neutralization. Now, my own opinion is if I were to put this on the test, it would be a bonus question because I'm not actually going to teach it to you. It is a unit that I was taught, but molarity has become the one everybody uses. But does anybody happen to take it? Anybody happen to know the last one? What is it? Molality. And again, I would not go home and stress on that because if I were to put it on there, it would definitely be a bonus question. Get that? Now, we did a lot today, and all I'd like you to do is to take this sheet home, and if you want to redo some of the problems, you say, what was that thing he was talking about? Molarity of the hydroxide ion? And then before we take the quiz tomorrow, I'd like you to be able to have a chance to ask some questions. You get that? All right, so we don't have a big test tomorrow. We have a kind of smaller quiz. We moved the test to Wednesday. And, okay. All right, well, thank you very much. You did a great job today.